Hi, everyone. Welcome to today's session on multi-messenger astronomy with Rubin Observatory, or what I think of as the TO session. Our goal here today is to talk about some scientific opportunities and the sort of associated technical challenges that come with trying to execute TOs, especially in sort of the commissioning, early operations era for Rubin. I'm joined by Raffaella and Margutti, who is co-chairing with me. And we'll start actually with Raf sort of giving a session intro.
All right, yeah, it's very exciting to be here. It's my first conference after the pandemic. So yeah, I'll start with a very short intro and just taking us to the beginning, the first time that the scientific collaborations actually formally proposed the target of opportunities as a observing modality on LSST. This is all the way back to 2016, back to when the GW follow-up subgroup only had a few members that you can see listed there. Right now we are way more. And if you want to join, please reach out to me. So after that, we all know that something really important happened in 2017 with GW 170817 with huge impact on every sort of science. But the real question that I want to attack with you today is, what is the future? So all of us know that all of these great impacts of 170817 in these very different branches of physics were fundamentally enabled by one thing, which is the identification of the counterpart. So where in the sky should I repoint my telescopes? So, and what I want to discuss with you today is where are we now? Where is the frontier of discovery after 170817? And here I'm going to identify a few directions, definitely not all the directions, but a few of the most prominent directions. And the first point is, of course, we have n=1 event, for which we have gravitational waves and light. We would really like to expand this sample to be a sample, so population studies, to understand the diversity of these binary neutron star mergers. The second point is about trying to find new components of emission, and here I am emphasizing the origin of the blue component of our kilonova, but also trying to find new emission components that we might have missed for 170817. And of course, another huge place for discovery is counterparts of black hole neutron star mergers. That is something that we have observed in the gravitational wave world. We have yet to find a counterpart, and that's definitely one of the things we would really love to do with LSST. And then point number 4, there is still speculation about counterparts of black holes mergers, and I think that's a place where the depth of LSST can play a key role. So let's not forget about these black holes that are merging. And last but not least, it would be nice to find counterparts also to unidentified gravitational wave sources. So if we try to understand what do we have to do to really get there and really make the most of this discovery phase space, well, we will clearly very soon realize that we need 2 ingredients. We need to go deep, so sensitivity is the first keywords, and we need to go on target very fast. So we need to repoint promptly. So those are the 2 ingredients that will enable effectively multi-messenger astrophysics going forward. And here, I just want to end with this slide where I want to make the point that sensitivity is really the key here. LSST, the depth that we will reach is really the key that will allow us to find EM counterparts of neutron star mergers and black hole neutron star mergers. Here in this slide, you have a number of kilonova light curves for some range of parameters at different distances. And you can clearly see very quickly that the 1/d sensitivity scaling of the GW world is already winning a lot over the 1/d squared sensitivity of everything that tries to detect stuff on the EM world. And you can clearly see that facilities like this DTF will actually not be sensitive enough for us to find these counterparts at the typical distances where gravitational waves will actually identify them. So this is about this future that we want to talk about today for the rest of the session. And I don't want to take up more of your time, and I leave the podium to somebody that Eric is going to tell me.
Yes, before we go to deep, actually, we're going to invite Bob Bellm, the operations director, up to say a couple words of introduction as well.
Hi, good afternoon. This is just a quick few words about some context of what's been happening with some of the data products and how we envision connecting them to the community as we go forward into operations. And the context is important for what happens in the rest of this discussion that Eric's leading on how we can be most effective with transients and TOOs as we go through this end of commissioning phase into early operations, where we're still working out how to best do things. So to remind you, of course, we will put out alerts every 60 seconds as we observe the sky, and that hasn't changed. That will come with postage stamp images and information that will be in a database available to anyone who is connected to the Rubin Science Platform. That's no matter where you are in the data rights holders ecosystem. But the agencies have given us guidance about the timing of release of other data products as we go forward. And so basically, any images, any full images related to those alerts on a nightly basis will be held for 80 hours. Now, we've worked with the project science team and others in the community to understand if there's a scientific impact here. I certainly wouldn't tell you that there's no scientific impact by doing this, but we think it minimizes any major impacts on the scientific cases. That's something that we will continue to discuss as we go forward. A very few images might be held longer than 80 hours, and some perhaps indefinitely, but that should be a very, very tiny amount of data. As well as we go through the commissioning period, everything taken during the commissioning period, so when we're talking about commissioning camera and LSST camera, will be held for 30 days until it's released outside the project team that's taking the data. That includes everyone broadly involved in the commissioning activities, not just people that work for Aura or SWAG. But it will be held for 30 days until it goes outside. So that is another, these two things conspire to put perhaps constraints on how the community works with Rubin as we go forward in early phases, especially detecting, working on TOs and stuff. What is it that we need to do internally to make you successful externally? So I just wanted to set that out there as some new context that will be important in this discussion as we go forward. I'm not taking questions. No, go ahead.
Sorry, just a point of clarification. That's the full frame image?
That is the full frame images. The alerts will come out just as they've always been envisioned. The alerts with a postage stamp and the other ancillary data will be in a database. People can get that as soon as it's available in the database. And the alerts will come out in 60 seconds, go to brokers. Yep. Eric, feel free to cut this off because this was not the intent of this this session.
So, follow up. Events. I don't know. Pulse of light. So what I want to ask is, so we won't know from most of the announcements.
Okay, sorry. So it's important to follow up these events within minutes because we don't know very much about the physics of and that's the whole point. The point is with LSST to find where it is in the sky so we can pass it on within hours, actually, to spectroscopic follow-up facilities. And so we need the entire field because we don't know where in the field it is. And during that time that we scan the gravitational wave 90% confidence area in the sky, there are going to be literally tens of thousands of, I would say, ordinary transients, the things that we know and love. And we have to be able to separate those from the gravitational event. So that means looking at all of that area on a short time scale.
Yep, we're totally in agreement. And so what we're talking about here is how do we make that happen within these constraints? And we'll make it happen largely within the project with input and advice from the community going forward.
Thanks, Bob. All right, we'll come back to more of these. We are saving time for discussion at the end. So let's now switch to Deep Chatterjee, who's connecting remotely, who's going to give us an update from the LIGO Virgo Kagra collaboration. So go ahead, Deep. Yeah, I got your slides. Right.
Yep, thank you, Eric. Could you confirm that you can see my slides and hear me all right?
Yes, we can. Go ahead.
Perfect. Thank you so much. So firstly, I would like to thank Eric and Raf for inviting me over to the Rubin PCW to give this talk on the LIGO Virgo Kagra observing plans and alerts in O4 and beyond. I'll also like to mention that I'm giving this presentation jointly with Fred Raab from the LIGO Lab, who has also joined online with me. So before I get started, I do want to share some pointer to where you can find the most recent observing timeline information. So if you go to LIGO.org here, and on the right there's this tab called Observing Plans, and under that you would find the most up-to-date information, and not just that, you would also find some helpful links to what is the current observatory status, so on and so forth, in case you're interested. And that's also updated every couple of months. But if you went there now, you would find a timeline like this. So this purple over here is O4. As some of you may know, the start date of O4 is March of 2023. It is supposed to be a 1-year-long observing run with a 1-month gap in the middle for a break. And the number on top here is the average sensitivity to binary neutron star in spirals for these gravitational wave detectors. So there is a significant improvement from for both the LIGO and the Virgo detectors from O3 going into O4. During O3, the LIGO detectors were between 100 to 140 megaparsec. That's going up to 160 to 190. And for the Virgo detector, likewise, the improvement is from 40 to 50 up to 80 to 115 megaparsecs. And then the Kagra detector that joined at the later stages of O3, they'll be joining at the start of O4 with slightly better sensitivity of around greater than 1 megaparsec, but they'll be breaking for commissioning during the observing run and rejoin at the later half of the observing run with around 10 megaparsec sensitivity. So that is O4, and looking at O5, the dates are still tentative. The timeline that we are looking into now is 2026. However, more concrete dates would be announced as we come closer to that time frame. So what are the expectations? As we all know that the gravitational wave discoveries have been steadily growing with every observing run. O1, we started with 3 binary black hole discoveries, and that number rose to 10 in O2, plus the 1 binary neutron star, GW170817. And then at the end of O3, we stand at a cumulative total of 90 events. However, the interesting ones, which is the ones that involve matter, that fraction, unfortunately, has gone down compared to if you were standing, say, at the end of O2. And not only that, during O3, the more interesting ones were discovered at farther distances and also with larger sky localizations compared to 170817, which made the EM follow-up really hard, and unfortunately, there was no EM counterpart discovered. And so even after 5 years, GW170817 still remains the only success story of EMGW astronomy. But the hope is going into O4 with both the LIGO and Virgo instruments much more sensitive. We'll not only get more number of events, but hopefully there would be some of them which will be interesting as well as better localized. And so in terms of detection rates, in O3, if I take the average detection rate, it was 1 per every 4.2 calendar days. The hope is that in O4, it would be 1 every other day. And by the time we reach O5, it would be more than 2 per day. OK, so here what I'm showing is the alert timeline. So what happened, at least during O3, what happened after a gravitational wave was discovered. So the process starts off over here in the top left corner with the real-time searches, analyzing the data, finding new candidates. There is some automated vetting, some initial source classification and source properties are computed. A rapid sky localization is computed. All of that is packed into a machine-readable notice and sent over the GCN network as a first preliminary alert. And parallelly, because there are multiple search pipelines uploading multiple candidates, all of that has to be clustered into a single physical entity, re-annotated, and a second alert would be sent at that point. And it is at this point that there would be human involvement in the loop. So observatory staff would look at the state of the detector, and they would either approve the event as an initial alert or retract the event. And if the alert was approved as a discovery, then it would be followed up in days to week time scale with more refined data products in terms of sky maps and source properties from parameter estimation results. So like this, a total of 80 public alerts were sent. 56 of them were non-retracted. Most of them made its way into the catalog. And a lot of this structure will also port over to O4 with some new changes that I'll be talking about later in the presentation. Okay, so what I'm showing here is the latency of the alerts as a function of the observing runs. So the very left over here is O1, when there was no automated alert delivery system. O2 was the first time when there was some automation put in place, but the alerts were not public. And then in O3, that effort was ramped up. There was more infrastructure to deliver the public alerts. And what we see from here, and I want you to focus on the orange bars, is that the latency has been steadily going down, especially towards the later stages of O3. The alerts were sent at or even less than around 5-minute time scale. The hope is that in O4, we will be able to bring that down to 1 minute, maybe in some cases around 30 seconds for the so-called full bandwidth analysis. And then on the extreme right, there are some negative latencies here. And what that is the so-called pre-merger or the early warning alerts. And I'll have a slide later on it, but essentially that is an alerting mechanism before the merger has happened. And that has been demonstrated on not on real data, but on mock data post the O3. And that will be a deliverable going ahead in O4. Okay, so in terms of alert content, there is information that directly comes out of the searches, which is the search information, whether the search is modeled or unmodeled, the significance, the timestamp, which in case of the modeled searches is the time of the coalescence. And then there are the annotations, like the sky localizations, the source properties, which are captured by these two quantities called has-ns and has-remnant, which captured the chances of having a counterpart. And then the astrophysical classification, which are these numbers that sum up to 1. And going ahead in O4, there will be some improvements done to these. For example, for these source properties, has-ns and has-remnant, there will be more realistic equations of state that are taken into account when reporting these quantities. And also in O4, the mass cap category would be removed from here and put into the source properties here. And also, as and when more updated parameter estimation results are available, these quantities are updated on the update using the update notices. Okay, so of course, O4 is going to be a scale up from O3, predominantly because of the detector sensitivities. And like I mentioned, we expect a detection about every other day. And in terms of a total number count of BNSS, we expect order 10 BNSS during O4. All right. So in the next couple of slides, I'll talk about what is new. As I had mentioned in a previous slide, this early warning alerts, which have already been demonstrated, the concept here is that since binary neutron star signals are longer, lasting almost up to a couple of minutes in the frequency sensitivity of the detectors, as they evolve in frequency, they gain significance, and if at any point of time that is enough to claim discovery, one can send the alert when the binary is in spiraling, so that there are still tens of seconds to capture the prompt emission. And most compact binary searches have developed an early warning search, and the expectation is that will be deployed during O4. Another change is the underlying platform which is used to deliver these alerts. So traditionally, the LVK has distributed alerts over the gamma ray coordinate network using these legacy VO event format. However, going ahead, I think there is already a talk about the new GCN, the General Coordinate Network. And then there is also the scalable cyber infrastructure for multi-messenger astrophysics, both of which have developed tools to distribute alerts using modern tools like Apache Kafka, which is also used in the Rubin community by the broker teams. And so the going into O4, apart from the legacy VO events, we will also be streaming alerts using these alert services. Another new thing in O4 is that the SkyMap format, we are going to be recommending the multi-order coverage SkyMap as, or rather, this will be the preferred format of the sky localizations. What this is essentially an adaptive subdivision of pixels, so that well-localized events, the SkyMaps for those are not very big. These are, with the multi-order coverage SkyMaps, they are smaller in size, and therefore we can pack them into the alerts and send them as a part of the alert, which is also a change from previous observing runs where we would send a URL for the external observers to pull them down from. But now we'll pack them as a part of our alerts. In terms of software support, since this is an IVOA recommendation, software like Aladdin already supports handling of this format. But at the same time, the LIGO.SkyMap library is available for all our SkyMap handling, for all of our SkyMap handling. And also the legacy FITS files will be available in our database, which is called GraceDB, in case anyone wanted them. I do want to mention that some of these early warning alerts may not have a sky localization, and that is for certain science cases where they only require a timestamp and not a localization. But whenever a sky localization is available, that will be delivered, and that is true even for the early warning alerts. And finally, there will be the external coincidence search. So these are searches done between gravitational waves and external triggers like high-energy neutrinos and gamma ray bursts and supernovae. So we'll have the Llama and the Raven pipelines. And here the use case is that if there is a subthreshold gravitational wave event in coincidence with one of these external triggers, that may elevate that subthreshold trigger to an otherwise public alert level. And in that case, the revised significance along with the combined sky maps like this will be sent out. Okay, so with that, I think it was a short talk. I'll just conclude by inviting everyone here to the Open LVM forum. These are periodic and public remote participations. You will get to hear detector updates, run planning, and updates on alerts. The latest one was in last month, so please check out this wiki page. And I do also want to mention that it's not just the LVK that participate in it, but members of the broader community, including the Rubin community, that do participate in this. For example, there was a nice talk by Graham Smith from the Lensing team in Rubin in the last call. And also, we are thrilled about O4 and also excited that Rubin is already thinking about the TO program. Folks like Tiago had already reached out to our alerts team, and I'm sure that we'll be talking more in the next few months to come. So with that, I'll thank you all, and I'll take questions whenever it's appropriate. Thank you.
All right, thank you, Tiago. I think what we're going to do is we're going to hold questions for the discussion period to make sure we have enough time for that at the end. So we're going to go to a series of talks from a variety of folks looking at technical and strategic aspects of this, starting with Tiago, who is back there.
My slide here, the next one? Does my slide here? Yeah. Okay. Hello, everybody. So I only have a single slide. There you go. So the idea, I want to talk to you about the technical aspect, how we're going to handle TOs. A couple people reached out to me the last couple of months saying, some of them were a little bit desperate, saying, oh, are we going to handle TOs? And the answer, yes. We have requirements of the observatory control system that we have to handle TOs. There was nothing actually implemented so far at this point, like actually implemented on the responding to TOs, because it was not on the timeline for us to do it. But a lot of the machinery we need to respond to TOs is implemented, and the idea is integrated to the control system. So basically, I started to talk to people from the SEMA group that handles the output of the events, and people from LIGO as well as, sorry, I forgot his name. It's just talking. And the initial design that we came, we want to be we want to leave the problem as least constrained as possible, so we can handle different constraints that the community ask us to be able to handle. So the idea is basically that so this is an overview of the system here. We have the DDS bus there. It's been hidden by the bar. That's basically how the components on the observatory control system talk to each other. So the system has several components to actually be able to handle observations. And the two key components here is the scheduler CSE and the script queue CSE. So CSE is basically a component on the system. And the scheduler is a machine that digests telemetry. So it gets telemetry, runs it through the scheduling application or algorithm, and the algorithm tells it what to do next. And then what the scheduler does, it sends that publishes that information to the system, and then the script queue will catch that and then execute the observation, right? So the place where the scheduler gets telemetry from is the EFD, which is the Engineering Facility Database. So all the telemetry from the observatory is written on the EFD, and the scheduler can already query that information and use that to produce targets for observation. So the idea is we'll have, when you have several producers in the system, the producer is basically a component that can write data to the EFD. And the idea is that we'll have a TO alert producer. So it's a component that will get the alerts and basically write them to the EFD, and which allows the CSC, the scheduler, to get that information and digest it. Now, what is in that alert is still open. Of course, we should be able to handle the LIGO alerts. We don't have the schema for that alerts yet, but we are working with them to get that information so we can start digesting that information. And then what sends us that alert is still also open to discussion. We right now are working with SIMA group, which is one of the groups that was just shown here to replicate the alerts. But we are working with them to integrate their TO alert streams into this, have that connection between their stream and our TO alert producer, so we can output that data into the EFD and then be able to follow them. So there is a tech note that we wrote with an overview of this system. You can find the link on the slide, TSTN 35. It's fairly technical on the observatory control aspect. And it's very open-ended in the sense that we're not trying to constrain the system too much at this point. So there are places here for the operators to intervene. There are places here for the project to intervene to tell us how many TOs we can respond and set thresholds and all that machinery either exists or is planned to be developed and added to the system. So that's basically it. So the idea is we'll be able to handle the TOs. We want to be as responsive as possible. So if the minute time scale fits into the observatory control requirements, we usually are one visit behind, meaning the next visit, while the telescope is observing one visit, the next visit we are already decided what's going to be. It's a requirement of the system. But that means we can respond basically in 30 seconds time scale to an alert, meaning that we need to add that information into the EFD for the scheduler to digest it. But as long as that is met, we can respond pretty quickly. And we all know the telescope is really fast, so we can turn around pretty quickly. And yeah, I'll be here all week if you have questions. I have a session today about the observatory control. If you want to come up and see what is beyond the scheduler and the script queue, well, come and talk to us. Thank you.
Thank you, Tiago. Again, we're holding questions, or feel free to put them in the Slack chat. Next, Lynne Jones is going to talk about some of the simulations of survey strategy and what they mean for TOs.
Thanks, Eric. So this is not necessarily quite as interesting as how are we actually going to point the telescope at the thing, or what science are we going to get out of it. But what these simulations were intended to do was to evaluate what is the effect on the rest of the survey if we do spend some time responding to TOs. So so we ran some simulations. If you're familiar with the OpSim, it's basically we take we create a 10-year pointing history of the telescope using some choices for survey strategy and a realistic weather distribution. And then we get out, like, what would the telescope actually do for those 10 years? So we have our baseline survey strategy, and this is what we would be comparing to in this case where we add an extra stream of alert events. So we ran two simulations, one where we added 10 TO events per year. That's 6.6% or about 2.6% of the survey time was actually used for the events that we were actually able to successfully observe. They're randomly distributed on the sky, only attempt to follow up events where the center of the event is inside the full Rubin survey footprint. For the events themselves, we're just sort of assuming that we need to cover a circle, a 6.5 degree radius around each event. And then for the survey actual observing strategy, it's observe at times of 0, like at the trigger time, 1 hour, 2 hour, 4 hours, and 8 hours after the alert. All of the, this is following a survey strategy from Margutti et al. And it was a white paper as part of the, I think this was the 2018 call for white papers. So it's following that strategy as closely as we can. The white paper, we had to make a few modifications to meet requirements of the telescope. So we do 30-second exposures with the 5 filters that are actually available at that time. to complete one cycle over this 6.5 degrees radius circle takes more than an hour. So this might be something that we need to go back and look at. The pointings are just like plastered on the sky, so, and then repeated. So there's not really an attempt to dither or do rotational dithering, even to fill in the chip gaps. Okay, so I should actually, sorry, I in the process of taking my these slides from the original place into the big shared presentation, I did forget to add a comment on the previous page, which was that Peter Yoakum, who is part of the survey scheduling team, was has created these simulations and done most of this analysis and actually made most of these slides. So I should make sure that I give him plenty of credit for this. In fact, he's the person you should talk to when you're trying to refine this survey strategy for TOOs. So when we look at where these are in the sky, the visits, so you see two sky maps there. These are sky maps that come out of math. The one on the left is if we do 10 events per year. The one on the right is if we do, the title is wrong. It should be 50 events per year. And then on the bottom right is just sort of a visualization of one of these events that got all of the observations that it wanted. And this is where they were located on the sky. The X at the center, which you can't see because this is in the way. Let me get rid of it. Nope. Okay, there we go. The X at the center of this little plot is where the TO center of the event was, and then we plastered around that location. And there we go. Out of the injected events, about 50% got any observations. You might expect that, right? Some of them are out of the footprint, some of them are on the other side of the sky, or there can be in cloudy conditions. So if about 50% get any observations, if you were to complete the full set of observations, it would take about 500 visits. And at the top here, you see plots of how many follow-up observations you get per TO in both, on the left, the 10 per year, and on the right, the 50 per year simulations. So you can see that many of the TO triggers only get a few observations. Some get the full 50, and many, many more are just somewhere in the middle. Most of this is because of the field we don't do anything particularly smart in the scheduler when the event comes in. So the field might be about to set. We might be about to be interrupted by some other downtime. That there are, for example, weather events that happen in the middle of the night. So there's a variety of reasons why they might not get the full 500 events, but very often it does happen. And given that the time span for this is 8 hours, that is quite and it would be 9 hours by the time you're finished with that last set. That is quite a long time span, and I really wouldn't expect a large fraction of them to be able to observe for that long. However, there is some good news. If you look at the sky maps of this coverage at the end of the survey, after 10 years, the scheduler is compensated from the fact that we had these sort of maps, chickenpox maps maybe, on the sky. And so the sky coverage is even, no residual artifacts in survey footprint coverage. And the impact on other science is mostly minimal. Probably we could minimize that further if we did things like not actually start observations for the events we couldn't take any observations of, although that would then drop the fraction of things that we followed at all. There are some other possibilities. So on the right here, what you see here is what we call our radar plot. The blue line is the baseline. So you can see there's a blue circle that's just hitting 1 all the way around because these metrics are normalized to the baseline. The green line is when there's 50 events injected per year. And so you see nothing in the 50 events per year, nothing falls lower than, even about 5% when you normalize the metric. And in the 10 per year event, there was something that was hit a little bit harder. So that's probably just something random about where the events were versus where the other metric was placing events on the sky. So the good news here is that it does look like this can be folded in with the general survey strategy.
Next is Federica Bianco to talk about the survey cadence optimization aspects of this.
Hello, my name is Federica Bianco. I'm the Deputy Project Scientist for Construction, and as part of that role, I have the responsibility of chairing the SCOC, or SCOC, as some of you have called it, the Science Cadence Optimization Committee, which is charged with making recommendations on the cadence that Rubin will actually apply on the sky once operation starts. The SCOC is a committee of about 12 members. I want to acknowledge them and recognize them. They have a huge responsibility to make this recommendation that can really make or break our science cases for the observatory. The full members are on the left. There are two ex officio members, which means we are non-voting members, and one of them you've just heard from is Lynne Jones, and the other one is me. The SCOC also, the individual members are assigned to the science collaborations as liaisons. So they have the charge with that role of keeping the science collaboration informed about what we're doing and what input we need, and bringing their input to us. Also, of course, core to this team is the observing strategy team as a whole, and I want to acknowledge them as well. So the process, the SCOC was funded in about 2020, and the idea is we get input from you all, the community, we analyze that input, we fold it into rules for the observatory on how to patch the sky. And this is obviously a very difficult process. It's an optimization process, but it requires domain knowledge and expertise, and it requires you all to contribute the information to us. The committee's big deadline upcoming is in December 2022, when we will deliver our recommendations for how to start the survey to the director, Bob Bellm. And you see here a fairly cheaply drawn timeline of events leading up to that. And right now we are at the first blue point at the PCW in August 2022. We will have a workshop in November to connect one more time with community directly, but also we are open to feedback and communication with the community throughout. These are the decisions that we are making, the topics that we're considering in our decision process leading to the recommendations, and the only one that you care in this room is number 7 down there, the time allocation for TOs. So finally we get to that. But the truth is that that is intertwined with a lot of the other decisions that we're making. It's particularly intertwined with early science, which we TO as a microsurvey, and there are other microsurveys. So, and it's intertwined with all the work that you heard of until now. How can we implement TOs, and particularly what is the proper strategy for TOs? What is the scientific throughput of a strategy, which we then can compare with the impact on the survey? So, as a long story short, what we're expecting to do in our December recommendation is to deliver to the observatory director an envelope of time that we can spend on TO without impacting the other science. And you've already seen it, because you've already seen that we have the simulations that Lynne has just presented. You've seen that that's possible. Also, of course, though, that depends on how the strategy for TOs is implemented. So certainly the devil is still in the details of that as well. But we can provide that, and we can provide input on what is the framework that LSST should adopt for response to TOs. And so As part of that is how do we respond to TOs, which TOs do we respond to, what is the actual strategy that we implement, alternation of filters and positions in the sky, etc. To converge on this, we are thinking of proposing to the relevant parties, to the experts on TOs, on the second aspect of what is the actual strategy that we will implement. We're thinking of setting up a workshop for people to come together in the room and give us, as a deliverable of that workshop, a set of recommendations for the actual implementation of the follow-up. And right now we're foreseeing that that will be in early 2023. And that should tell us how we select the TOs, how we follow up the TOs on a scientific basis, so that then we can implement it on the technical basis. I think I'm done.
Thank you, Fed. I'm actually going to now present a little bit about data processing of TOs and the feedback process to some of the decision making we've heard about. So drawing a little bit on Bob's emphasis, just a reminder that alerts are Rubin's real-time data product. And so we expect that when the survey is running at full speed, normal TO observations, as long as they are similarly left to standard survey observations, will pass naturally through the alert production pipelines and produce alerts. They will go to community alert brokers within 60 seconds. I think everyone has heard that there have been 7 alert brokers with their logos here selected for full stream access. And so science users should expect to, again, in steady state operations, to think about TO follow-up that are making use of these community alert brokers. However, the challenge is in the commissioning and early operations phases before we have templates. So it takes time to take enough images of the sky and all our filters to have good templates. LSST images are heavily dithered, and it frankly just, it takes time to get good images. So during sort of the commissioning phase that overlaps O4 in particular, there won't be widespread templates available, and so standard automated alert production simply won't be possible, at least unless we're extremely lucky with a gravitational wave going off in a field that we've been observing for 2 months. It's just a very compressed timeline. So what can we do to get the science out? Well, first, of course, we will build templates as fast as we can. We call this incremental template generation because normally templates are made during annual data releases, but during, again, that commissioning and early operations period, as the images come in each night, we'll look at them and say, given the quality and spatial coverage of these, we can make a new template here. Now we can make a new template here in this filter. And as those templates build up, we will begin, again, standard automated alert production on those as they become available. There are a variety of complicated technical pieces. Some of you were in the DIA session, and we talked already about this in terms of making sure that we have the right balance of spatial coverage and good seeing and artifact rejection and all of those sorts of things. But I think the message here is just that we will make templates and good templates as soon as we can and get the alerts out as soon as we're able. However, again, we want to be able to exercise the TO capability. The images, we can't just throw those over the wall as Bob described. I think 170817 provides a good example that you don't always need image differencing to find a counterpart. Admittedly, that was a lucky case, but here are a bunch of examples of counterpart identifications without image subtraction. So the proposal that we are considering is that the Rubin staff will attempt to, on a sort of best effort basis, do some manual processing of TOO observations when they're taken in this early phase to try to find counterparts, and not to try to do the science, but to get the data out to the community so that you can do the science in a similar sort of vein as automated alert production. This is, I would say, not a scope that is super well established in, for example, the operations proposals. So we have to be a little thoughtful about how much we promise here in terms of the available effort. This involves waking people up in the middle of the night, having them on call who might not necessarily want to do that every night or every other night, as Deep described. So that implies some degree of prioritization in terms of what TO observations we take at all. And then just to summarize, these sorts of trade-offs and discussions are summarized at more length in this tech note RTN 008 if you are curious. All right, so finally let's go to Igor Andreoni, who's going to talk a little bit about potential for making scientific use of this challenging period.
Hi all, and thank you for having me here today. Indeed, I would like to tell you a little bit about how we can convert all this amazing technology into actual science and to discovery. If you want, you can see the process distinct in two components. The detection component, which of course involves selecting, first of all, which gravitational wave follow-up you want to activate your telescope for. You want to be rapid, as Raffaella reminded us, so that we can catch these fast-evolving transients. You probably want to observe the field of interest multiple times at different time scales so that you can capture the evolution of a full grid of possibilities in your parameters. And perhaps you can even play with the exposure times of your observations. But then comes what is the real discovery component. As Tony was mentioning, we already are, during current follow-up with our facilities, we're inundated with trends that are irrelevant for this science case. So discovery will happen when we manage to tell which of the many transients in the field is the one we're interested into, or looks like it, and is not one of the other many transients that will be present in the field. So this is the philosophy behind our attempt to develop strategies that are mindful of all these aspects and can help us maximize the science. Commissioning can really be important for the success of this effort. And commissioning with both the commissioning camera and, of course, with the LSST camera. Definitely what we want to do, first of all, is to keep refining the workflow, because even a perfect design for a machine will always need some iteration in the process, and we do need it to be smooth if we want to succeed. We want to perhaps improve the interaction with the scheduler if needed, so just we are sure that whatever we would like to implement definitely agrees with whatever are the policies of Rubin observatories and the technical capabilities of the scheduler. Definitely doing dry runs on fake alerts can truly help make sure that we can go from top to bottom in as many cases as possible. And they're all different from each other. They always have some surprises for us. And most importantly, there is an opportunity here, also in the overlap between the very beginning of commissioning and O4. And this could be really good for early science. Again, with the commissioning camera, that we have a very small field of view, we can still do multi-band transient characterization of a discovered counterpart or of many transient, and then help the community distinguish which one is the counterpart we can associate to a gravitational wave source. Or we can implement a galaxy-targeted search strategy. There is a lot we can play with here. And definitely, we can do that in an even better way with LSST-CAM. And why not? Since this is a field that is still so new, so rapidly evolving, we can then further improve our strategies, because experience will teach us literally from one event to the next. So what I would like to talk about now is just we're offering a possible strategy that a pretty big fraction of the community, especially from the TVS collaboration, but also other people from other collaboration, put together based on the white paper that Raffaella Margutti led in 2018. But also we enriched that with the experience matured during the recent O3 observing run. In particular, what we would like to see its multi-band observations as rapidly as possible in at least 2 and possibly 3 epochs in the first night that transient happens. That can enable discovery, as we said before. And why not even distinguishing the fastest evolving transients from all the background and foreground sources. But of course, then ideally we would like to see observation taken even on the following night and possibly 2 nights after that if the counterpart is not yet discovered. So this way we maximize the possibility to find the transient, even if it's rapidly evolving, distinguish it from the background sources, and why not get some great science for free, especially in the first few hours where there is a lot of interesting physics that we can do, but not often enough we would be able to trigger follow-up observations on the spot. And the strategy could be tweaked also depending on the classification of the gravitational wave trigger. For example, if a neutron star black hole merger occurs and not a binary neutron star mergers, it's more likely that would be more mass in the ejecta, and the light curve is likely to appear more red and more slowly evolving. So again, experience taught us that we do have to have some flexibility in our way of doing follow-up. And of course, the more we make these decisions up front, the more we can automatize the process and the better we can do the science eventually. And this can be true even in case of binary black hole mergers, about which we really don't know little in what comes to electromagnetic spectrum. So perhaps the later phases of the evolution of possible transients associated with the event would be covered, let's say, automatically by the survey. However, TO observations might be needed to cover the very first hours where, once again, we don't know. Perhaps there is an interesting counterpart that would be otherwise missed, and we don't want to miss out on the unknown unknowns. Lynne has already extensively talked about some simulations that were carried out to understand the impact of the observations on the rest of the survey. I hear actually very often people talking about how many hours TOs will take away from the survey. But I would recommend to also take a different metric into account. In fact, people have worked so hard from the community to develop science verification metrics that can tell us how well can we do a given science based on a certain cadence. So if you look at those metrics, the impact of TOs can be as small as less than 1% in most cases. And Lynne talked about more than 57,000 visits for 50 triggers per year. This is very unlikely is going to happen, and LIGO and Virgo are not on every year. They are on usually at alternate years or so. So the takeaway message here is that we expect TOs to be very little disruptive for most science cases. So what do we need? In this slide, I put in red whatever I wish to see ready already during commissioning. And that includes, of course, a system that allows us to connect the triggers from gravitational waves to where the magic happens, perhaps. So the observing planning phase. When do we trigger? How do we trigger? And then, of course, transmit this information to the scheduler. And also from a very interesting conversation, brief but interesting, I had yesterday with Tiago, is my understanding that perhaps can also the scheduler kind of inform us how we can further optimize the plan such that we can maximize the science, minimizing, once again, the impact of the main survey. We definitely would like to see some image processing happening. And thank you, Eric, for saying that you are considering alternative methods for doing image subtraction or source detection, even without templates. We can also use other surveys that are out there. They're pretty deep, magnitude 24, like Legacy Survey, or even models like the tractor models that were developed and are used in other projects as templates. So looking forward to hear more about that. But absolutely, please, let's make sure we have as much coverage in templates in as many bands as possible, as soon as possible. And finally, I would just recommend, let's develop some tools for performance evaluation so that we can make sure we can do that the observation we're doing not only work from a technical point of view, but the images we took can actually allow us to do the science we want to do. And many of these tools have been developed during O3 and hopefully can become routinely used during O4, O5, and during the life of Rubin. Do I have one more minute, or should I just leave it here? So just to summarize what I said, it's easy to talk about the importance of multi-messenger astronomy, but to be able to do multi-messenger astronomy, we really need that discovery part to be there. And it's not enough to have the most powerful telescope on Earth. We really have to use it well. And that's what I would really like the community to come together and help make sure this happens. Fortunately, we can implement at least a set of images taken during the observations in the LSST survey. This will allow most science cases not to be damaged at all, not to be affected by TOOs. Once again, commissioning is a very precious time. I really hope most of the systems will be already in place for that, and there is interest from the leadership to invest in this effort, because in the end, this can be low-hanging fruit for pretty good science and pretty soon in the project. Thank you very much for your attention.
All right, thank you, everyone. Thanks to all the speakers, and we have now 30 minutes for a Q&A and discussion. I got a request from Leo Singer to say a couple of words about these slides. So Leo, maybe you want to go to that mic there. I will just drive you through here. And then I will attempt to, with Melissa's help, triage questions. Yeah, just. Oh, okay.
Any successor.
Button in the back. Here, Leo, you come up here while.
Right. So the Gamma Ray Coordinates Network is this alert distribution system and collaboration platform and astronomical bulletin board system that's been in operation for now about 30 years, used by the gamma ray burst community very heavily, and also has been used for communicating about LIGO follow-up. The general coordinates network is sort of the modernization of the system. So we have a new website. It has an updated look and feel. It has this single sign-on system. But I think the most important thing is that it allows you to, now you can manage your subscriptions to what notifications you receive yourself through the website. The other big thing is that the new general coordinates network is built on Kafka. I convinced my colleagues at NASA that, it's been clear for, almost a decade now that LSST was going to adopt Kafka as its way of distributing its primary public data products, and there are a multitude of facilities that have been following suit, and so it just seemed totally obvious that to me that the sort of next iteration of GCN needed to be based on Kafka. So there's the legacy gamma ray coordinates network we're now calling GCN Classic. There are these three legacy alert formats. So right now the LIGO Virgo public alerts are sent to GCN in VO event format. GCN converts that to these other legacy email and binary formats. So beforehand, there were sort of 3 different custom protocols that you had to use to talk to GCN. Now you just connect via Kafka. And in the not too distant future, we're going to try to develop a unified multi-mission schema that will allow you to get alerts from essentially all NASA missions and hopefully also from LIGO in a single alert format that is hopefully very similar to the LSST alert format. And that's it. Thank you.
All right, I am triaging questions. The first, I have a couple for Bob. I don't know if you want to come up here, Bob, or go to the, here's fine. There are a couple questions basically around, we've focused here on GWTOOs, because that's the near term sort of high pressure thing, but what are your views on other, solar system TOOs, other sorts of, what does that sort of decision process might look like in the operations area?
That's a really good question. So I think we have focused around gravitational waves because I think there's a unique need for integration between the community and Rubin to be successful in this one case. And I think there are other TOOs that are scientifically very interesting, and I think we should try and accommodate their observation, but I don't think they need to be quite as integrated into the observatory. And so what I would envision is that we work with the SCOC and the survey scheduling team to understand what is the total capability that we want to, and that means working with the community. What is the total amount of time we want to put into TOOs? And those other ones that are not as uniquely need the direct integration with Rubin, let's put them through a science time allocation merit review. Let's do it at Noir Lab like any other science-based proposal to any of our other telescopes. And then let's make the allocation. So the advantage there would be the proposing team gets to get their science done and gets to lead it. Of course, we would make sure that all the data are from any TOO program are immediately available to everyone in the community, just like all the rest of the Rubin data.
Thanks, Bob. Let me go next. There was a question to Fed about SCOC members rotate off at the end of 22 and there'll be new members in 23. Will those folks be in place by the time of this workshop? You could just go there if you want to. It was. Maybe it turns itself off. Still in a second. I think the batteries are dead.
Yes. Yes, we expect the transition to be sort of seamless and to replace about half of the members with new members. The SAC is in charge to find the new members, but we do not expect to have a gap between the two commissions, and we have continuity on the committee.
Let me open the floor for now to other questions. Yeah, Gautam, well, sorry. Why don't you just shout and I will repeat the question.
LIGO issues in the Rubin. It would really help to have LSST publish its schedule to something like LCO's treasure map service, so everybody else knows where LSST is pointing. And B, have the scheduler respond to where everybody else is pointing, so you don't repeat observations that are unnecessary unless they're significant. You have to have 3D information in the sky map during redshift. So somewhere LSST, I would love to actually see bite the bullet and make a science-based decision process to which galaxies are potentially in the right redshift frame to follow up. And you have DES in the south, start doing this already, and you will have BR1 after a year of operations to get better for.
I clearly should have let you speak in the mic because now I have to try to repeat that for the folks who are remote. That was a great point. Gautam said basically that the procedure outline is very one way. The alerts come in from LSST and from LIGO and Virgo and Kagra, and LSST goes off and observes. But of course, there are other facilities observing, and they would like to know what Rubin will do, and Rubin might want to react to what facilities with broader aerial coverage and smaller depths, for instance, might be doing. I think that's all true. I'm not actually sure who on the project I should point to and say, this is your job to think about it. Maybe it's Lynne. I think that's one of the, Tiago says it's him. Yes. Yeah, Tiago says that we do have a requirement to publish our schedule, and it's presumably not too hard. I'm confident it's not too hard to connect that to the treasure map. I agree that we haven't contemplated the sort of deeper sort of science-based selection, and that's a feedback we've been getting from many folks, including I have a little experience from O3 as well, but that at least historically there has been more scientist in the loop sort of decision making, and that's not something that you're hearing much about here. Yes, I agree that there is the aspect of this that is sensitive is around the data access, and so folks who are embedded in commissioning in particular, that's sort of a natural place that we expect to look. That also raises some other concerns that I think need to be explored, and certainly what things look like in steady state is also, I think, so there are lots of pieces there, but I agree that we need scientific experts close to the data and not just, just the technical folks. Mario, shout and I'll repeat.
For various, both for multi-messenger observatories and for follow-up observatories where you can basically get them all at the same place and exchange data. So if we, for example, with LSST, publish into the stream of here's what telescopes are going to observe, it becomes trivial to connect it to any other downstream service that actually tries to do something with it. So I guess the point here is that there are efforts in the community to solve these problems, and integrating or communicating more with Rubin and other projects may kind of help us get together.
All right, I will hope that most of that was remote accessible. Tiago, maybe could you run the mic up to Leo here? Yeah, go ahead and hop in. Yeah, you go ahead and do that mic if you can.
Mario adjusted the mic for his height, not mine. So I have a couple comments. I guess on the last on the point about how to decide what triggers or what gravitational wave events to trigger on. I'm a little, so I guess I feel like it would be good to have some capability for manual selection of triggers, at least initially, because what is suitable to follow up is going to depend a lot on where those rolling reference images are available. And also, I mean, it already stated that you stop, you terminate the TOO once the counterpart is identified, but it's actually not always, it's generally not that straightforward to tell when the counterpart was identified. In the case of 1708-17 it was, but it's more often a very, very tricky judgment call. Also, LIGO retracts events frequently. They publish updated localizations, which sometimes can mean you might replan the fields that you want to look at. You might you may want or might not want to do that replanning in a way that optimizes overlap with fields that you've already observed. And there are different things that might involve, making a judgment call. So a couple other things. So in Lynne's talk, the TOO simulations were based on circles with 6.5 degree radii. I mean, we have a lot more information about what localizations of LIGO events will look like, and I think it'll be great to start using some of that. Also, the distance information in the localizations is useful for more than just selecting events. It's also useful for deciding how many exposures you want for each field, because the distance estimate actually varies spatially across the sky. So I'm very much interested in what goes into that box that translates the events into an actual TOO.
Thanks, Leo. It's all great perspective, and I think that I'm certainly hearing that there's tons of material for this potential 2023 workshop for us to work through these details in extreme detail. Let me take a question off of Slack from Steve Ridgway, and then I see Stephen Smart has his hand raised. Steve Smart asked about public crowdsourcing as a way to get eyes on candidates. I think that's a great idea. That one of the challenges is that we're not, again, by definition, running automated processing, so that makes sort of setting up a flow to public eyes a little more challenging. But again, our idea here for this early phase is just to get candidates out to the science community as quick as we can. All right, Stephen, do you want to maybe try to unmute and ask your question?
Yeah, can you hear me okay?
Yes, we can.
Yeah, it was just a comment, yes. And thank you for picking up on it.
Oh, sorry. I'm going to Stephen Smart. Sorry.
Yeah, that was Steve Ridgway just thanking you. Yeah. So, I mean, lots of good points made here, and Leo pointed out how complex this could be to make good decisions. The workshop next year will obviously be very important, but I'm wondering, this is a question I think for the project, it may well be worth setting up a working group to work on it. I mean, if we have a workshop, we'll all get together, make some decision, maybe write something, but I think there's probably work to do for a working group on an ongoing basis during 04 to see what happens, maybe towards the end of 04 with potential commissioning time. And we had the precedent for this, of course, is the Euclid Rubin derived data products group, which got together and made some decisions and recommendations. I mean, I think there's a lot of complex issues here. It's extremely valuable time. We want to use it well. I think the project should consider setting up some sort of working group because it's an aspect of the SCOC, but it's too detailed, I think, for them. And it may require a more focused working group to help the project out and help the community make these decisions.
Hi, Steve, that's Raf. So we actually have a working group, which is the subgroup that GW follow-up is a part of the TVS. And as you know, we have been in communication recently. And I think it's a group that will play an important role in advising about what is the best strategy. And it's my first priority to make sure that that group will actually represent what the community wants and not just what a few people might prefer.
So I'm asking something different. I appreciate that, Raf, that committee. I think that it should be a project-led. The project should appoint a committee that is across several science collaborations. I mean, that's a good bottom-up committee. It's led to Igor's had a fantastic paper out. Again, that's a bottom-up thing, but I think to link directly with what the project will do and can do, and there will be an envelope, there will be constraints that the project put on this if we do TOOs. So I think that's a good initiative, but I'm asking something else from the project, which is a bit higher level.
I will certainly say that I think it's clear that we need to improve, continue to improve our internal organization in the project. Tony, did you have a question? Why don't you go to the mic?
Yeah, I agree that because of this data security issue, there has to be somebody on the inside who's qualified, actually, to run this whole detection and analysis routine in less than 80 hours on a very short time scale. I'd just like to make one point, and that is that in the time domain, the most valuable thing that's going to come from the LSST is the discovery of the unexpected, and this is a perfect area where I think we want to be prepared to discover the unexpected, or at least avoid not discovering it. And for that reason, I'd like to propose that we look, at least initially, not forever, but initially, on everything that has a signal-to-noise ratio greater than 20. We don't know what we're going to find, but we know that for those events, the error circles on the sky are going to be small enough that we don't spend forever covering it multiple times. The biggest problem is this huge foreground from variables. So we have to, in any case, we have to cover it multiple times.
Thanks, Tony. All right, Tiago wants to make a comment, and then I'm going to let Raf give us a summary to close the session.
Thanks, Eric. Yeah, so I was just talking to Mario, he reminded me. So we are actually in the process of designing the system that feeds the data, the alerts from SEMA to the summit, and being able to process them and follow up. We were going to do a run this month on Oxtel to follow up a couple of events, but there was a snowstorm at the summit and everything is shut down. Maybe have heard that. So we are waiting. As soon as the summit is open again, we already have the pipes connected. We got the data from SEMA to a EFD instance here in Tucson, and we are able to process that data already. So as soon as the summit is up, we're gonna connect that final pipe and do a live test. Hopefully, be able to successfully run and get a fake TO. Thank you.
All right, thanks, Tiago. All right, Raf, why don't you summarize and we'll close the session for today.
Right, yeah. So first of all, I would like to thank everybody for being here, here in person, and all of you that are participating online. I'd like to thank all our speakers. I'd like to thank Eric for putting together such a great session. I want to close with a very positive note. We started in 2016 with very few people that were caring about TOs, and a lot of people against us, saying that will never happen. That's something that LSST will never do. It's fantastic to be here today to discuss the fantastic science that will come out of LSST, and I think the future is just fantastic ahead of us. So thank you very much to everybody.